Alright, this is Mr. Gillum, and today we're going to continue on with trigonometry and learn a little bit about inverse, sine, cosine, and tangent. So what we have here is the inverse trigonometric functions, and obviously they go with their corresponding trigonometric parts. Sine goes with inverse sine, cosine goes with inverse cosine, tangent goes with inverse tangent, obviously, okay? Now there's a lot of words here and a lot of confusing things that look like, okay? The big thing to know is that when you take something to the negative first power, now you may or may not have covered this in algebra, when negative exponent basically moves the base to the bottom of the fraction. That's what it does. So when you raise something to the negative first power, it's really the inverse. So we would write the inverse sine as sine to the negative first power, inverse cosine, same thing, and inverse tangent. So when you hear me say inverse sine, you're thinking sine to the -1. Basically what each of them does is they undo their base, their original trigonometric function. So I'm just going to draw like some simple equations. Now they might not be true, but they're just examples of equations when it would be appropriate to use the inverse sine, inverse cosine, or inverse tangent. Usually, what we've done in the past is we had like sine of 35 equals x over 2, and then we were able to solve for x. Okay, when we have the angle, that's fine, but what's going to change today is that the angle will be the unknown part. We don't know how many degrees the angle is, and so in order to undo sine, we can't just divide both sides by sine. Obviously, we have to use some sort of inverse operation. So kind of like addition and subtraction are inverses, and multiplying by the reciprocals using the inverse of the fraction. Same thing here. We're going to take the inverse sine of both sides of this equation. And so the inverse sine leaves us with x, and so then we would have to calculate the inverse sine of 2/5. And when you type it in your calculator, make sure that you do also type it in parentheses. Depending on your calculator, that fraction may be left behind. So I'm going to type in my calculator the inverse sine of 2/5. And it gives me 23.58. So if you have a calculator in front of you, you want to double check. Might be good just to make sure you know how your calculator operates. Again, also make sure your calculator is in degrees. We have not learned about radians yet, which would be RAD. So if you see the DEG on your calculator, then you're in good shape. The cosine and the tangent work similarly to that. If we had the cosine, we had the cosine of some missing angle that we don't know equals to whatever fraction we would take. We would find the inverse cosine of each side to undo the cosine of x. Their inverse operation, same way with tangent. So let's take a look at the next part here. It says use a calculator to find the measure of angle A to the nearest tenth. So similarly, in this case, we don't know angle A and angle B, and we need to know what angle A is. So this is my unknown. I could use the Pythagorean theorem, something, to find this missing side right here, but I really don't need to know it. With the given information, there's plenty. Knowing what we know about our trig functions. So these are the ratios of the trig functions. So I see that if I'm referring to angle A, I have an opposite side, and they also give me a hypotenuse. So if I find the sine of angle A, it would be equal to the ratio of the opposite over the hypotenuse. In this case, 18 over 27. Now ideally you'll reduce that fraction and continue to solve the problem. 2 over 3, and it's just a matter of undoing using inverse operations to solve the equation. So I'm going to type the sine, inverse sine of both sides, and so when I type that in my calculator, 2/3, the inverse sine of that is 41.81. So I'm going to say that angle A equals 41.81. It does say to the nearest tenth, right there. So I'm going to erase that one right there. 41.8 degrees. All right. So very similar to yesterday, except for now we're just adding this inverse operation to help us solve our equations. Yesterday we were setting them up more like proportions. Today you'll need inverse trig to do this. I'm going to just erase this so I have plenty of room here. Okay, again, we're always trying to find angle A in this case. It's just what the directions say. We can find any angle that we really want to, though. In this case, this is angle A, and so the two values they give me are opposite of angle A, and in this case, the adjacent side. And so when I look at O and A up here, I see that they're in TOA, so I'm going to, that's just a little way to remember. The tangent of angle A must equal the ratio of the opposite divided by the adjacent side. And I always like to reduce my fractions, so we're going to say that's 3/10. And my inverse tangent will undo tangent. So A must equal, my calculator says 16.7. Okay, this is always representative of an angle. When you're finding the trig using sine, cosine, tangent, you're finding the ratio of the angle compared to the side lengths. So finally, we have angle A, and in this case, it gives us an adjacent side. And again, an opposite side. And so this would be the hypotenuse. It's a funny looking diagram. Okay. Yep, that's fine. So in this case, they actually give us the adjacent side and the hypotenuse. It's going to be a tricky one. Okay, so adjacent and hypotenuse tells me we're probably going to use cosine using that ratio. We'll say the cosine of A equals 3/15, the adjacent side over the hypotenuse. And again, I'm going to simplify or reduce because it's just how I am. And I'm going to use the inverse trig to undo. So I know that A equals 78.5 degrees. All right. Let's take a look at the next part here. It says when you use given measures to find the unknown angle and side measures of a right triangle, you're solving the right triangle. When you solve a right triangle, you need all the side lengths and all the angles. So in order to do that, you need at least 2 side lengths, or one or the other. You need at least 2 side lengths, or you need a side length and the measure of one acute angle. Okay, now given these are all right triangles, so we always know that there's a one right angle. So really it's 2 side lengths and a 90-degree angle, which we already know, and 1 side length and 1 acute angle, which would help us to find the last few. And so what we're going to do is we're going to solve these right triangles. So an example of having 2 side lengths would be this guy. 2 side lengths, we don't have any other angles, nothing like that. Or we could have 1 side length and one of the acute angles, as well as our right angle, of course. So one of those 2 things has to happen in order for us to solve the right triangle. In this case, we're going around to the nearest tenth, and angle measures to the nearest degree. So side measures to the nearest tenth, angle measures to the nearest degree. If I'm going to solve this, let's see, I have a 90-degree angle. I just need one of these other angles, and then I can use just algebra to find the last one. Also, I can just use the Pythagorean theorem to find this last side length. But what would be the fun in that? Let's use some trig to find them. So, actually, for the sake of time, I think we're going to have to use Pythagorean theorem and that type of thing. We just need all the side lengths and all the angle measures. So, I know that since this is a right triangle, of course, leg squared plus leg squared is the hypotenuse squared. And so 25 plus 81 . The square root of 106 is our hypotenuse, and it does say to round to the nearest tenth, so instead of getting the exact value, we're going to use 10.3. Okay, so we found our last missing side length. I also need to have at least one of these angles, so I'm just going to pick angle Y to solve for. I could have picked angle X. It doesn't really matter which one. And I can use any trig that I want because I have all those side lengths now. Using the ones they give us that are actually whole numbers. I see I have an opposite and an adjacent side. So I want to find the tangent of y, angle y. It would be equal to the opposite over the adjacent side, 5/9. I could do the sine. It would be opposite over hypotenuse. It just, this would change and the ratio would change. Use any trig function you want or any trig part you want. That's fine. And it's just a matter of using inverse operations to solve for your answer. Y equals 29 degrees. And I'm rounding here. This is 29.0546041, but it does say to round to the nearest angle. So measure of angle y is 29 degrees. And because there's 180 degrees in a triangle, if I have 90 used up and I have 29 used up, then there's 61 left for this guy. Okay, so make it clear that you know all the angles and side lengths. I'm going to say xz, even though it was given, is equal to 5. zy is equal to 9. xy is equal to 10.3. Angle z is my 90. Angle x is 61. And angle y is 29. All right, so now I've solved the right triangle. I know all of its proportions, dimensions, all of its side lengths, everything that I need to know. Again, let's take a look at this one. Just because I have two angles and a side, I can solve for the entire triangle. I know that because there's 180 degrees in a triangle, that there must be 28 degrees left for him to be. Okay, so that's half the battle right there. We've got all of our sides taken care of, or our angles taken care of. Now we need to use trig functions to find the missing lengths. So we can use 62 this time if you want. I know that I have missing an adjacent and well, to 62 I'm missing an adjacent and an opposite. So I would like to pick a trig function that has only one or the other in it. And so my strategy is going to be, well, if I use the hypotenuse somehow, using so or ka, I can find one of my missing. So that's what I'm going to do. I'm going to say the sine of 62. That's the ratio between the opposite. In this case, we don't know. We'll call him x and y. And the hypotenuse, 10. And this is just like yesterday. I set up as a proportion, and I'm going to cross multiply. I'm going to say the sine of 62 is 0.8829. I'm going to times that by 10 or multiply that by 10. It says round side measures to the nearest tenth. So my answer, my solution would be x equals 8.8. I'm going to say this side right here, BC, 8.8. And then finally, using trig again, or I could use the Pythagorean theorem at this point. I'm going to use trig, I think. If I use the cosine of 62, that would be the adjacent side. In this case, we don't know what it is. Why? This is the adjacent side of 62 compared to its hypotenuse, 10. And again, cross multiply. 10 times 60 cosine of 62 is 4.6947. I'm going to round that to the nearest tenth as stated in the directions. 4.7. This guy's 4.7 now. I have a big blotchy marker today. So what I'm going to do is I'm going to make sure that it's clear that I know I've solved the entire right triangle. I know AB equals 4.7, BC equals 8.8, and AC equals 10. I also know that angle A is 62, angle B is my 90 degree, and finally angle C is 28 degrees. All right, that's it for today.